Okay, this is going to be the video for AP Statistics, Chapter 21, which is about Type 1 and Type 2 errors and the power of the test. Okay, so does our analysis that we do, now that we know how to do confidence intervals and hypothesis tests, we're actually testing some sort of a conclusion, which means we make a statement based on probability that something is either we have evidence for an alternate hypothesis or we do not have sufficient evidence for that. But does that analysis always come to the correct conclusion? Let's take an example of this type of problem we've been considering about DV seniors staying in state for college. Let's say that the DV counseling department records show that in the past, 78% of DV seniors attend state college in state. And then we ask a simple random sample of 50 seniors this year, and 42% of them stayed there, staying in state. Do we have reason to believe that more seniors are staying in state this year? Okay, so if we were to do this using the Chapter 20 techniques, we would say we need hypotheses first. HO and symbols would be that P is equal to the historic percentage of 78%. And since the wording more is here, we would say the alternate hypothesis is that P is greater than 0.78. And if we were to do this calculation by hand, we would figure out, okay, what happened in our sample was 42 out of 50, which was 84%. That's certainly higher than the historic value, but we have to use the sampling distribution of the sample proportions to figure out if that's unusual, right? So we make the assumption of the null hypothesis value at 78% here in the middle. We use the formula for finding the standard deviation of a p hat value distribution, and that would be PQ over N, so 0.78 times 0.22 over 50, which is 0.059, which means that then our particular value of 84% here that we had this time is above, but we can calculate the p-value of that happening randomly if the null hypothesis was true. So we would do normal CDF from 0.84 to infinity with 78% as the mean and the 0.059 as the standard deviation. We get 0.15, which means with a p-value of 15%, there's a 15% chance of this particular sample result happening randomly. That's not unusual enough for us to reject the HO. So we say we don't reject the null hypothesis. And we conclude, just to be more precise here, we would say something like, we don't reject the null hypothesis. And we would say, all right, therefore, we do not have sufficient statistical evidence to conclude that more seniors are staying in state this year. To be more precise, that's the format we would say, right? We don't have evidence to conclude that more seniors are staying in state, which means kind of, more generally, we're saying the percentage that are staying in state is still 78%, okay? All right, so that would be the way we would do the analysis. We feel like that's correct. That's all correct. Okay, but what if we did this? What if we just increased the sample size? Same year, same set of students, same population, but we took a larger sample. So let's say that this time we took a sample of 200 seniors and 168% of them said that they stayed in state, which is the same 84%, right? So the same percentage in the sample. We go through the same hypotheses. One thing that's different though is because the sample size is larger, the standard deviation for the sampling distribution is lower, right? Where before it was 0.059, now it's a lot narrower. We have a higher sample size, so there's less variability from sample to sample. And that means now that the standard deviation is only 0.029. And so when we redo that, the distance here has not changed. What's happened is this has gotten a lot less wide, right? Before it was way out here. Now it's a lot less wide. So this same standard deviation, this same value is more standard deviations away. And so our p-value drops below the magic 0.05 number, right? Same value, but when we had a sample size of 50, that value is only one standard deviation above the mean. And now that we have a sample size of 200, just because of the fact that this is narrower means that same value is now over 2 standard deviations above the mean. So now it crosses into unusual territory, and we would change our write-up. We'd say with a p-value of 0.019, that's low, so we reject HO. Therefore, we do have sufficient evidence to say that the percentage is higher for this year. So what gives here, right? Same students. The only thing we did was change the sample size, and the result of our conclusion completely changed, right? So what happened? Did we make a mistake? The first time we had a wide standard deviation, that same value had a big p-value, but the second time with a larger sample size, we have a narrower standard deviation. So now we are under 5%. So in a sense, this kind of came to the wrong conclusion, right? It was the same data, same population, but just because we took too small of a sample size, we kind of came to the opposite conclusion. Now that we looked at a bigger percentage of the population, I guess we would say this is more likely to be true, right? Because it represents a bigger part of the population. But we didn't really do anything wrong here, right? It's not actually wrong. It just came to the wrong conclusion, right? Okay. With the larger sample size, we did determine that the percentage of seniors staying in state did increase, but there wasn't anything wrong with our first analysis. So although we didn't do anything wrong in the first analysis, we have to conclude that the first analysis failed to reject the null hypothesis, even though there really was a difference. In other words, um, when we looked at a higher sample size, this was up here, which suggests that this p-value, this population value, is really not here. It's probably up here, because even when we took a larger sample size, we still got values up here. So this is probably not where this is not where the true value is. It's probably somewhere up here. Okay. All right. So even though we didn't do anything wrong, the first analysis failed to reject the null, even though the null hypothesis was in fact false. There was a difference. That is referred to as an error. Doesn't mean we did anything wrong. It's just a standard statistical term. That means that the analysis came to the wrong conclusion. And that's going to happen when you base things on probability, okay? So there are two types of errors. One's called a type 1 error, and the other one's called a type 2 error. A type 1 error is when the null hypothesis is actually true, which means there is nothing to detect here, nothing has changed, but our data just happens to be randomly so far away that we get a low p-value, so we incorrectly reject the null hypothesis. And a type 2 error is when the null hypothesis is actually false, because there is something to detect. There is a statistically significant difference, right? But our data just happened to have a value that was close to the null hypothesis value. So we got a high p-value, and we incorrectly failed to reject the null. Okay. Okay, to keep this kind of straight, we have a little kind of a picture that you can draw. You can make a little table here. First of all, the columns are what happens to the null hypothesis, right? Is the null hypothesis actually true, or is it actually false? And then based on our p-value, we make some sort of a decision. If we have a low p-value, right, we reject the null hypothesis. And if we have a high p-value, so a value below 0.05 or above 0.05, we fail to reject the null hypothesis, right? Okay, let's say we had a low p-value, right? Which means we rejected the null hypothesis. That would be the right thing to do if the null hypothesis is false. If the null hypothesis is really false, the right thing to do is reject it. That's totally okay. Similarly, if we had a p-value that was above 0.05 and we failed to reject, if the null hypothesis is true, then that means that's the right thing to do. So that's okay. So these two quadrants are fine, right? But on the other hand, if the null hypothesis is true and we reject it, then we're doing the wrong thing. And this box up here represents type 1 error. If the null hypothesis is false and we don't reject it, that's the one that's called the type 2 error. So that's down here. Okay. So this is to kind of help keep us straight. We can draw this little diagram over here. Now, what this alpha and beta stuff is the probability of these things happening. So by definition, we call the probability of having, let me use red because this is about errors. The probability of having a type 1 error occur is defined to be alpha. And the probability of having a type 2 error occur is defined as the symbol beta, which is like the B in the Greek alphabet. Okay. All right. So we're going to look at these things in a little bit more detail by using one of those those phone apps that we have seen. So let's take a quick look at this phone app. If you go to mrfelling.com/SA4 in a web browser on your phone, you'll get to this page right here. Okay. All right. So what we're going to do is enter the following numbers here. We're going to put 0.78 in for the population proportion. We're going to put a sample size of 50. We're going to indicate our significance level, which is called alpha, which is when we start deciding that something is unusual enough to be, or low enough probability to cross over and be considered unusual. And then we'll just say that the null hypothesis is true. We'll just leave that checked. Okay. And then we'll click sample. Okay. Now, when we do this, we're showing a population here. We set it so the population percentage is 78%. 78% is yes, whatever this is. And let's do this in context of DV seniors. So what we're saying is that historically, 78% of seniors are staying in state for college. Okay, this year's seniors, we took a sample. We took a sample of 50, and this year's percentage of seniors is maybe not exactly 78%. This time when I ran it, I got 82%. The time when I made these slides, I got 76%. You're going to get some other value because we know at the sample level, it changes every time I take a sample. So I get my p-hat value here, which is represented as a dot. Okay, and that sample is just one of the possible samples, right? So when we calculate the p-value, what that means is we're going to assume that the sampling distribution is centered at the null hypothesis value of 0.78, and our particular value that we got of, let's say in this case, it was 0.82, means that this is just one of the many possible samples of distribution here, right? So let's go ahead and take many samples by clicking the sample 100 times button. Okay. All right. So there is some value out here where if the p-hat value happens to be further away than that, above this, because this was shaded to the right, then that means that the p-value would drop below 5%. Okay. That particular value actually is called the critical p-value. And we'll talk about what the symbol is for that in a second. But that means that randomly, we might get some values, the p-hat values that are varying around up here, right? They may happen to occur way out here. And if that happens, then the p-value is going to be really low, right? Which means that we would reject the null hypothesis, right? Okay, but when we entered this program, we said we're going to assume the null hypothesis is true. So what that means is it was actually incorrect for us to reject that null hypothesis. So all of these analyses out here that are marked in red, these are marked in red because they came to the wrong conclusion. The null hypothesis actually was true. The percentage of DV seniors that stay in state this year really is still about 78%. And yet randomly we have a p-hat value. We just happen to get a sample of 50 students that's way out here at 90% stayed in state. If we use that particular sample to do our analysis, it'll come to the wrong conclusion and error, right? All these other dots here represent different samples of 50 students that had a proportion value that was closer to the null hypothesis value, so much so that their p-values were above 5%. So they all came to the right conclusion that we should fail to reject the null hypothesis. And so these all came to the right conclusion. So we did 100 trials here, and 6 of them came to the wrong conclusion. And that means that 6 out of 100 times our analysis committed a type 1 error, right? We had a null hypothesis that was true. Let me go back in here in the notes and show you this. We had a null hypothesis which was true, and yet we rejected the null because randomly we had some value that was randomly way out here. So we came to the wrong conclusion. The null hypothesis is really true, but we rejected it anyway. So this 6 out of 100, 6% of the time, we came to the wrong conclusion and committed that error. All right. Okay, so what is the probability of having a type 1 error? Well, that's actually really, really easy. It's just going to be what percentage of the time are these p-hat values going to land on the other side of this line where there's a 5% chance of rejecting, of it happening by random. Well, that's completely determined by whatever we choose alpha to be. So if we choose alpha to be 0.05, like it usually is set for, the significance level of 0.05, then that's also the probability of committing a type 1 error. The probability of committing a type 1 error is just whatever we decide our decision point is when we decide how unusual something or what the probability has to be below before we consider it unusual. So if we go with the standard, anything less than 5% chance of happening randomly is unusual, then 5% of the time we're going to commit a type 1 error, or we were going to come to the wrong conclusion just randomly. Okay, so that's how a type 1 error works. Let's look at a type 2 error. Let's reset, and then we'll set the simulation to be the population proportion. Let's set that to be 0.86, which means that this time a type 2 error is when the null hypothesis is actually false, which means there really is a difference in the DV seniors that stay in state this year. So it's not 78%. The real true population value in DV of percentage of people going to college in state is really now no longer 78. It's really all the way up here at 86%. We're going to leave the sample size at 50. We're going to leave our alpha value, our decision-making level of 5% for declaring something unusual. But this time we're going to set the null hypothesis to be false, and we'll indicate that we're still assuming that the null hypothesis is 0.78. In other words, the historic value is 0.78, and that's what we're assuming for the null hypothesis. But unbeknownst to us, the real value is something higher, like 0.86. Okay, let's click sample and see what happens here. Okay, so that means that, right, we assumed 0.78, which means that this distribution is centered at our null hypothesis of 0.78. But because the real population is up here at 86%, right, whenever we take samples, if I take a bunch of samples here, these sample values are typically going to be kind of coalescing around the 0.86 number. Right, so if I put a bunch of dots in there, in fact, if you click the 100 times button, you're going to get that there's a bunch of trials here, right? And they're going to all be kind of centered around the real population value, which is 86%, right? However, we didn't know that ahead of time, so we still assumed that it was the historic value. So when we calculate the p-value, we're going to be centering the sampling distribution on the null hypothesis value. And that means there is some sort of critical value here. It happens to be right about here, where there's a 5% chance. That's where we start going below 5% for p-values on the distribution that's centered at the null hypothesis value of 78%. Okay. All right. So then what that means is all of these values out here are doing the right thing, because we would actually have a low p-value and we would reject the null, which is what we should do because the population really has changed. It really is 0.86. Okay, so all of these values out here came to the right answer. But every once in a while, even if we have a population that's centered at 86%, because this sample can randomly vary, sometimes it's going to just randomly be low. And if it's randomly low, it's going to be sitting close to the middle of the null hypothesis centered sampling distribution. So we'll come up with a really big p-value and not reject it, even though we should have. So that means everything on the left side now is actually an error. Right? So what would the probability of the type 2 error be? Well, in this case, just kind of experimentally, 58 out of 104, which is 56% of the time we got it right, and 44% of the time we got it wrong. And so we have a pretty high probability here of committing a type 2 error. It's really hard to analyze that other than with simulation, because here's the problem. In order for us to compute this number, we have to actually know where these samples are really going to land, which means we would have to know how far up away from 78% the reality is for the student body at Desert Vista, right? We don't really usually know that. Okay, but anyway, this is how a type 2 error works. Okay, so there is some value out here on this curve. Let me use I'll use green. Actually, let me change colors here to something else like purple. Okay, so the null hypothesis, this is the curve we're using when we calculate p-value. So there is some value out here where we start getting into only 5%, but that's based on where we're assuming the null hypothesis is, right? This distribution over here, this thing is centered at wherever the reality is, where the real value is for the population, and we don't know that. right? So there's some boundary here, and anything on this side is okay, and anything on this side is an error. And it actually depends upon how far apart reality is from our null hypothesis assumption. All right. So you can kind of draw these kind of side by side to show what's going on, right? You have everything centered at the null hypothesis for calculating p-value. And that means that as you look at different p-values, right, the way we would actually do this is anything on this side, we're not going to reject the null hypothesis because this would have a large p-value. If we had a p-hat over here, we'd have a large p-value, which means we would not reject the null, right? On the other hand, if you took anything on this side of the line, and you had a p-hat that landed over here, you would have a really small p-value, and therefore that means you would reject the null. So we reject the null on this side, we fail to reject the null on this side, and everything is determined by where we assumed the null hypothesis to be. Okay, actually, let me back up that. Okay. Right, so what that means is there is some value here, right here. There's some value right here where we start going below a p-value, the probability value of 0.05. And that value there is called p star. It's called the critical p-value. That's when in the hypothesis test, we begin to start rejecting the null. Okay, so we can kind of visually show what the probability of a type 1 error is. The probability of a type 1 error is wherever we set alpha. Wherever we set alpha is going to determine that. Okay, the probability of a type B error is you would have to know how far away the actual value was from the null hypothesis value, and that difference is known as the effect size. And then you'd have to take that same value and figure out what's the probability if it was centered out here of having a p-value land in this region. So this is the probability that we call beta, the probability of a type 2 error happening. Okay. And then if you look at that bottom one, well, what happens on the other side? If this is a type 2 error, right over here, then this part over here means we did the right thing. There was an effect to detect. And we correctly rejected the null hypothesis and said we have evidence of the alternate hypothesis, concluded that that difference really existed, right? We did the right thing. And so there's a name for this probability over here. It's called the power of the test. And since beta plus the power of the test has to add up to 100%, the power of the test is always 100% minus beta. That's why in that box, I put that probability that way. So if you look in that box, a type 2 error probability is beta, type 1 error probability is alpha, and since the power is that the null hypothesis is false because there really was something to detect, and we correctly rejected the null to detect that the null hypothesis is false, the probability of that is 1 minus beta because these add up to 100%. There is no name for the probability of this. All right, so I know this is very confusing, but just stick with me and we'll get through it. And after you practice it a few times, it'll become a lot easier to understand. Okay. So you can use this to play around with different scenarios. You can try setting different effect sizes. You can try different things like what would happen, for example, if I decided to change the sample size. Let's take this exact same scenario here. You see how we had 56% power of the test over here and 40%, 44% chance of committing a type 2 error. Let's take all that same stuff, but let's just change the sample size to 150. Let's triple the sample size. So if we triple, actually, let's make it 200. Let's quadruple the sample size. So if we do that and we run through that same experiment, I'll just do this 100 times. What happens is that the standard deviation just goes down, right? So nothing changed about how big this effect was. This was still 86% really when we assumed 78%. But you notice how much narrower these two bell curves are? Well, they're so narrow that this critical value here, just about, in fact, every single sample we did was over here at the right thing and we rejected. So the power of the test went up to 100% because there were no errors. The way we got that was by increasing the sample size. Right? Let me go back to the original sample size of 50. Let's look at that again. Right? if I do a bunch of these, because this is now wider, these two bell curves are really overlapping. Here's where all the samples are really going to be. Here's where the bell curve is that lets us determine the p-value. And now quite a few of a lot of this bell curve is overlapping this. So there's a lot of cases where we committed a type 1 error. What else could we do to try to, say, reduce the type 1 error? We could reduce a type 1 error actually by, or sorry, reduce a type 2 error by increasing alpha. If we increase, actually, let's decrease this. Let's make it harder to judge something as false. Let's see what happens if I take alpha and I lower it to 0.01. So now you have to be only a 1% chance of something happening randomly before we say something's unusual. We're changing arbitrarily alpha. So what happens in that case? Well, in that case, what happens is this line, which used to be over here, moved out here. So it became a lot less likely for us to have probability of a type 1 error because we lowered alpha. But look what happened to the chance of a type 2 error because this line moved further out. Now there's fewer good cases and more worse cases, more bad cases. So we actually worsened our probability of a type 2 error. So I made this so you can kind of play around with different scenarios. You can try some things on your own. But I'm going to summarize what comes out. How can you reduce the errors? Well, if the original scenario was we had alpha set at the traditional 5% decision point for saying something's unusual, and the sample size was 50, we have quite a few power of the test where we found the right thing and quite a few type 2 errors, and there's a 5% chance of getting a type 1 error. Okay, if you decrease alpha, which is what we just showed over here, then that means the probability of a type 2 error, I'm sorry, a type 1 error goes down because that's just equal to alpha. But the trade-off is if you make alpha smaller, then beta always goes up. The probability of a type 2 error always goes up if you just decrease alpha. So you can trade off type 1 error versus type 2 error. You can make type 1 errors less likely to happen, but that will increase type 2 errors. The way that you can make both types of errors go down is to keep alpha the same, but increase the sample size, because if you can increase the sample size, everything gets narrower, so both types of errors go down. Okay, right. In fact, we can kind of summarize that this way. Let me summarize it this way. If you have if you're not able to change the sample size, so you have a fixed n, if you increase alpha, the result will be that beta will go down because the probability of a type error will go up, but you'll trade off and get a lower probability of type 2 error. And the power of the test, which is 1 minus beta, if beta goes down, 1 minus beta goes up. So you increase the power of the test, and you want the power of the test to be as high as possible because that's the likelihood you're going to detect the effect if it's there to detect. So one way you can improve the power of your test is by increasing alpha, but the downside of that is you're going to increase the chance of committing a type 1 error. If you can change n, then if you change n, the standard deviation goes down. And the fact that, sorry, the standard deviation, the sigma, standard deviation goes down. When these things get narrower, both alpha and beta go down because there's less overlap between the two bell curves. And that makes the power of the test go up. Right? So changing n always makes everything better. If you increase n, everything gets better. If you're unable to increase the sample size, you can make the power of the test higher, but you have to trade off making the probability of a type 1 error go up. All right. So why is this important? Well, it depends on the scenario. Sometimes one type of error is worse than the other. Sometimes neither of them are really particularly bad. So this example we've been looking at is about seniors staying in state for college, right? If we got it wrong, what would a type 1 error be in this case? So if I draw my little box out here, a type 1 error would mean that the null hypothesis is actually true. So this one is true, but we come to the wrong conclusion. So that means that the true percentage of seniors staying in state really is still 78%, but for some reason our analysis concluded that the percentage of seniors stayed in state changed or was different or something like that. Okay, not a big deal if we come to that. I mean, there's no lives hanging in the balance or anything like that. But that's what a type 1 error would be. What would a type 2 error be? A type 2 error would be if the null hypothesis was false, which means that this is not true, this is what's true. That's actually, there was a change in the percentage of seniors staying in state, but our analysis concluded that there was no difference from last year. Neither of those errors would be particularly terrible, so there's no particular reason to try to trade one of them off of the other. Okay, but what if I had this? What if I said I'm looking at a murder trial where we're going to put somebody in prison if they're guilty. So the alternate hypothesis is that the defendant or the prosecution thinks the defendant is guilty. The null hypothesis is the defendant is not guilty. So what would a type 1 error be? Well, a type 1 error would be that the null hypothesis is really true. So the defendant is actually innocent, but our court case convicts them and they are wrongfully sent to prison. That's really terrible, right? If an innocent person goes to prison. Right. On the other hand, a type 2 error would be that the null hypothesis is actually false, that this is really wrong and the defendant really is guilty, but for whatever reason, we set the person free. That's still bad, but most people would probably say that it's worse to imprison an innocent person than to not imprison a person who is guilty, because we might not have caught that person in the first place. So sometimes one type of error is more egregious than the other. Okay, and then to finish this, I want to show you an example. This is a made-up example, but it just illustrates what you would have to do if you wanted to try to really calculate the probabilities involved. So let's say that you're working on a machine, and there's a machine that produces a mechanical part that requires really tight tolerances for some tolerance critical application. This is actually taken from something from my days as an engineer when I worked on military radar projects. All the parts produced are measured and they have to be discarded if they're out of tolerance, which reduces the profit. This was actually true on one of the things I worked on. There was something that was so hard to produce that we just went ahead and let the machine make it. And then we inspected the parts and we just had to throw away the parts that were too short or too long, right? It was too hard to try to control it that accurately to make all the parts come out right. So all the parts are measured. They have to be discarded if they're out of tolerance, right? And then we have this machine and we test it periodically. And if it's found to be producing more than 10% of parts out of tolerance, then we go ahead and replace the machine, which costs even more. Right. So the latest batch of 200 parts from this machine contained 28 that were out of tolerance. Okay. That's 28 out of 200, which is 14%, which means that's above our 10% where we would say the machine, if the machine is consistently putting parts more than 10% bad parts out, it's time to replace it. This one test indicates maybe we're in that region, right? So is there sufficient evidence to conclude based on this sample that the machine's production of bad parts in general is above 10%? Okay, so we need a null hypothesis and an alternate hypothesis. So the alternate hypothesis here would be that the proportion of bad parts P is greater than the 10%, where we have to start replacing the machine. And the null hypothesis would be that it's equal to the boundary value where we would not take action. And we would do words typically here too, but I'm going to skip that so we can focus on the math. This particular sample was 28 out of 200, which is 14%. So that's some evidence that the alternate is true, but that's just in the sample. We have to determine what's happening for the population of all parts produced. Okay, we would figure out what the sampling distribution is, right? This is going to be the historic value for the null hypothesis value, so 10%. And we would have the square root of P times Q over the sample size, which was 200 parts, which would turn out to be 0.0212. And so we could use that to calculate a probability of this happening randomly if the machine is still in tolerance. So if the machine is still actually producing on average 10% bad parts, then the standard deviation from sample to sample of samples of 200 would have a standard deviation of 0.0212. Right, so this is 10, this is about 12, 14% from RP hat is somewhere out here. This is the null hypothesis value. And we could use this to find the p-value. We would have to do that with a normal CDF calculation. So we'd say normal CDF, and then we would say from 0.14 is the lower boundary to infinity, If the mean is 0.10 and the standard deviation is 0.0212, of course, we would label these lower, upper, mean, standard deviation. And that turns out to be 0.03, right? Right. So then we would write our analysis. We would say with alpha of 0.05, if I do my traditional, then the p-value of 0.03 is low. So we reject the null hypothesis, right? And then we would say we do have sufficient statistical evidence to conclude the alternate hypothesis that the machine percentage of bad parts is now over 10%, right? And we should replace the machine. Okay, so that's the kind of standard analysis there. Okay, nothing new so far. That's chapter 20 problem. But now let's talk about what a type 1 error would be. What would constitute a type 1 error? Well, let's draw our little box real quick. Our box is that the null hypothesis is true or false, and then we can either reject or not reject, right? This is okay, but this is a type 1 error and this is a type 2 error. So you have to memorize the pattern for this to be useful, right? A type 1 error happens when the null hypothesis is false. This is about the null hypothesis, is true. So if I look at this again, the null hypothesis would be true, which means the machine is actually still fine, but our analysis comes to the conclusion that it needs to be replaced. So a type 1 error would be the machine is still okay, but we replace it anyway. We think it's bad, so we replace it. Right? So we end up replacing machine before it needs to be replaced. The probability of that happening is called alpha, and that's just wherever we decided to do our analysis. So in our analysis, we chose 5% here. So that means there's a 5% chance that this analysis that we just did is going to result in us replacing the machine earlier than it needs to be replaced. And there's no way for us to know that really. There's just 5% chance. Okay, what would constitute a type 2 error? Now for this, we would actually have to know, we know here's the null hypothesis value that there's 10%. For this calculation, we would have to know, well, type 2 error is that the null hypothesis is false. So there must really be, the machine must be bad, right? So what is a type 2 error? A type 2 error is the machine is bad, but we don't detect it. So we keep using a bad machine. Right, the probability we have to calculate. And so to calculate that, we have to know what's called the effect size. We have to know, okay, how much out of tolerance is this machine? Okay, so I'm going to add something to the problem here. Let's make an assumption that we would have to have this somehow. Typically, we don't. Let's assume that the probability of a bad part in this machine has actually gone all the way up to 15% of the parts are out of tolerance instead of 10%. Let's assume that this is 15%. Typically, we don't know that, but for the purposes of showing how the calculation works, we'll assume we know it. If that were true, then we could figure out, okay, when would I start rejecting the null hypothesis? Okay, well, that's going to be whenever this probability here goes below our alpha level of 0.05. So I can use this centered at the null hypothesis value to figure out what the p hat value would have to be. That value can be found using inverse norm. That particular value is called p star. It's the critical p value. So I'll use that symbol. It's really a critical p hat value. We should use that. Okay, so that's going to be inverse norm. If we have 5% to the right, then there's 95% on the left side, area to the left. If we have 0.10 here, and this standard deviation is going to be the same standard deviation we calculated back here at 0.0212, calculated the same way. Okay, so 0.0212. So if you use inverse norm, 95% to the left with 0.1 in the middle, you get that this value is 0.135. So this value right here is 0.135. When I start having, so what this is basically saying is the machine would have to produce over 13.5% bad parts before the p-value would get low enough to cause me to reject the null hypothesis and say that the machine was out of tolerance. Anything less than that, I would conclude the machine is okay. Right, so what I'm trying to do right now is figure out the probability of the type 2 error. That probability is over here. So now that I know that this value is 0.135, and somehow I know that the machine's actually producing 15% bad parts, I can figure out how likely this is to happen. This is beta, the probability of a type 2 error. So now I can use normal CDF to find that. Normal CDF from negative infinity up to 0.135. If the mean was really 15% and we assume that same 0.0212 standard deviation, that turns out to be 0.24. So there's a 24% chance of having a type 2 error happen, meaning that if the machine was really out of tolerance and it was producing 15% bad parts instead of 10, there's a 24% chance that we would randomly not detect that. Okay. And then finally, we're going to calculate also the power of the test. So the power of the test is this probability over here. And that's easy. The power of the test is just 1 minus beta. So it would be 1 minus 24. And so therefore 76. So what we're saying is if a machine was 5% out of tolerance, if it was supposed to produce 10% bad parts and it was producing 15% bad parts, then there's actually a 76% chance that we would detect that using this analysis with alpha of 0.05. All right. Usually this chapter seems pretty darn convoluted, I would say, until you try some of the problems. But give it a try and really take advantage of this little box here to help you see what constitutes a type 1 error and a type 2 error. I've never seen AP ask to calculate a type 2 error except on uh, 1 year. There was 1 year they did it, and they ended up throwing out the question because they concluded that because typically students are not told this number, that it was too unusual. They ended up throwing out that part of the question. But I have frequently seen questions where they ask people to find the probability of a type 1 error. So you have to know that that's whatever you chose for alpha. Okay. And the most common thing of all on AP is to be asked to say what would constitute a type 1 error and what would constitute a type 1 error. So to be able to produce these sentences here, that's probably the most common thing that's asked here. All right, so just to summarize, right, your analysis may correctly reject a false hypothesis or correctly not reject a true false uh, hypothesis, but it's possible that that test will fail. The greater the effect size is, the easier it is to correctly see that effect, right? But it's really not possible to ever reduce the probability of these kind of errors to zero. This is the main reason why it's really good for when somebody publishes research for another team to independently conduct the research again, because when you do your one test, you're just getting 1 point result. And if that shows that something is either true or false, you would like another group to do that again because it becomes less and less likely that multiple analyses in multiple experiments would show that same error. Okay, so a type 1 error is when we reject the null hypothesis, even though it was true. And a type 2 error is when we don't reject the null hypothesis when we should have because it was false. Okay. The probability of a type 1 error is called alpha, the probability of a type 2 error is called beta, and the power of a test is 1 minus beta. All right, and then this is important too, to know what can we do to increase the power of the test, because we always want to make the test as likely as possible to detecting the effect if it's there to detect. One way is you can increase alpha, because if you increase alpha, beta goes down, and the power of the test is 1 minus beta, so that makes it go up. You can increase alpha. The downside to that is the likelihood of a type 1 error increases. You can also increase the sample size. That will increase sample size, decrease the standard deviation. This should be the standard deviation here. I'm sorry, no, that's actually correct. This will decrease the standard deviation, which therefore will decrease alpha and beta. So both types of errors get less likely and the power of the test goes up. So that's good, right? The other thing that can happen is if you're just trying to detect a bigger and bigger effect, that also separates these bell curves and causes the overlap that causes errors to be less likely. So just looking at a bigger effect size, right? And then the other thing you can do is anything you can do to decrease sampling variability by better accounting for sources of variability, like doing things like block design experiments or stratified random sampling, controlling other variables, anything you can do that reduces variability All that stuff increases the power of the test to detect the effect you're looking for. All right, and then that's it for chapter 21.